Hello everyone. In our previous class, we have discussed about group theory, the introduction class, and we have discussed all properties. Today, in this class, we are going to the identity and inverse property thoroughly. Okay, so that was our previous class. All the properties are there. Group theory 1, definition, properties. Okay, so move on. Today, we will discuss the identity and inverse property thoroughly. So, what is the identity? I have said to you that identity is such an element by composing which to any element would return that element. That is, if we say that E to be an identity element, then if we compose any A belongs to some group G to identity would return me that element, and that is this will happen for every A belong to the group G. So how we will interpret identity in the physical world? Let's take an example. Okay, so think that you have a bucket. It's a bucket, and in that bucket you have water in it. That's water. Think about a second that does water have any color? No, water doesn't have shape, water doesn't have color. It is unique. So, in this water, if we pour the yellow color, the water will become yellow. If in that water, before pouring yellow color, if we pour red color, the water will become red. So, water is like the identity element in the group that is returning that element by composing. We are composing a color into water and the water becomes that color. So I didn't think identity as the water in real world that shapes or colors to any color of that element. So identity can be many types, that is additive identity, multiplicative identity. If you have chosen the group as the integer with respect to addition, then you will have the identity element 0, because if you add to 0 any element, you'd get that element. So 0 is the identity element in the additive group of integers, and similarly if you choose any multiplicative group, so the identity would be 1. Let's take this, the positive integers or the set of all integers with respect to multiplication. Here the identity would be 1, because if you multiply to 1 with any element A, you would get that element. But this wouldn't form a group. Why this wouldn't form a group? Because you can find inverse of any element. Why? Because choose an element. Let's 2 belongs to the integer set Z, and you want to find the inverse of 2. So what will be the inverse of 2? The inverse of 2 is such an element A. Multiplying A with 2 would return the identity element of that set or group. What is the identity element here? The identity element is 1. So what you will get? You will get A equals 1 by 2. But you see that 1 by 2 doesn't belong to the integer set. So you can't find inverse of any element in this structure. So this is not a group at all. Okay, so for additive group, 0 is the identity element. For any algebraic structure with respect to multiplication, 1 is the identity element. So identity element can be many types. Okay, so let's discuss inverse property. Go to the next page. Inverse. Here a beautiful theorem we are going to discuss, that composition, inverse of composition, that is, if you have given A, composition B, whole inverse, then what will be the answer? You might think that will be A inverse composition B inverse. No, that will result in B inverse composition A inverse. It's similar as the matrix inverses. This is a property, this is not a coincidence. This is called the shock shoe property. So let's discuss that property. Wait a minute. Write it as shock, SHOCK, shoes property. What this property tells? It tells that for group elements, let's write it thoroughly. For group elements A and B, the inverse of AB, A composition B inverse, is equal to B inverse composition A inverse. Think for a second what is going on. Let's go back to the nostalgic days when we are going to school and we wear a proper uniform. So when we wear uniform, we first wear socks, then wear shoes. That is one process. Let shock be A. Let denote A. Let denote shock with A and shoes with B. So we first wear socks, then wear shoes. But when we return from school, we inverse this process. That is, we first open our shoes, then open our socks. We can't open socks before opening shoes. That is, the inverse of the first process is opening the shoes first, then opening the socks. So that is why this property is named shock shoes property. I think every one of you have understood this property well. And yes, this can be proved. This is not just a coincidence or any physical interpretation. This can be proved mathematically. Okay, so let's prove it. Wait a moment. Okay, so let's start. We first assume that the inverse of A composition B inverse is B inverse composition A inverse, and then we will show that yes, this is the inverse. So taking this, we composite, take A composition B and compose it with its inverse, that is A composition B whole inverse. What would it return? It will return the identity element of that group. Okay, so this implies A composition B composition B inverse composition A inverse, and this is what, by applying associative property, we get A composition B composed B inverse composed A inverse. And what is B composed B inverse? That is the identity. Okay, here's a mistake that we are going to prove this identity. We'll show these two identities, so we will not write it first. So okay, what is B composed B inverse? That is identity. So A composed identity composed A inverse, that is equal to A composed A inverse, that is equal to the identity element. So A composed B whole inverse is equal to the identity element. And what we have chosen A composed B whole inverse, that is equal to B inverse composed A inverse. So we have proven that A composed B whole inverse is equal to B inverse composed A inverse. So the property holds. So we have proved the theorem, that is A composed B whole inverse is equal to B inverse composed A inverse. This is proved. Let's go to the next page. Let us discuss about the real number set, that is R, the real numbers with respect to addition. Would this form a group? What do you think? Let's prove it formally. Let's take any two arbitrary elements a comma b belonging to the real number. We see that the addition with respect to the composition. What is the composition here? The composition is addition. So with respect to addition, a plus of b belongs to the real number, and it would occur for every a comma b belongs to real number. So our first, that is the closeness or closure property, is satisfied. The next property is associative property. So let A, comma B, comma C belongs to R, and we have A plus B plus C is equal to A plus B plus C. Again, A plus of B plus C, that is the change of parenthesis, that is also A plus B plus. So what we got? We got A plus B plus C, changing of parenthesis, A plus B plus C is equal, and this would hold for every A comma B comma C belonging to the real number. So the second property is also satisfied. Now we move on to the third property, that is finding an identity. So what will be the identity here? The identity is the zero element, because we have taken the composition as addition. So there exists an identity element 0 belong to the real numbers, such that for all A belongs to real number, A plus 0 equal to 0 plus A equal to A. So the third property is also satisfied. Move on to the fourth property, to find the inverse of any element. The inverse of any element with respect to addition is the negative of that one. So the inverse also exists. So for all A belonging to real number, there exists minus of A belonging to real number, such that A composition, the composition is addition plus minus of A, is equal to the identity element of that group R comma plus. So we see that the inverse of any element exists. So the fourth property is also satisfied. Hence we can call R the real numbers. The set of all real numbers with respect to addition is a group. Hence, conclusion, the set of all numbers with respect to addition forms a group. So our motto is complete for this video. We have discussed identity, we have discussed inverse, we have discussed the shock-shoes property, and we have proved an algebraic structure group. So okay, let's do one more. Let's think, if we compose here multiplication, would it form a group? That is what I want to ask. I want to ask, the set of all real numbers with respect to multiplication, would it form a group? The answer is no. Why no? It will be closer, it will be associative. There exists an identity 1 belongs to R, such that A into 1 equal to 1 into A equal to A. But what will be the problem? The problem will be, we would not find any inverse. That is, if we take any element 1, 2, 3, there will be inverses. But we have an element 0 also belonging to the real numbers. But what is the inverse of 0? Doesn't exist. That is 1 over 0. What is this? this doesn't exist. So we can't find the inverse of 0. That is why the set of all real numbers with respect to multiplication wouldn't form group. So what will form a group? This set, the set of all real numbers with respect to multiplication minus 0, excluding 0. This this set will form a group. So okay, let's stop the class. In our next class, we will discuss about the uniqueness of identity, the uniqueness of inverses, and from that class, we would go to the subgroups, then center of group, then cyclic group, Lagrange's theorem, and in all that. So okay, bye for now. Let's stop the class.